All right, problem 11, which is another problem to try to interpret a mechanism. In this case, notice that the mechanism has a reversible step at the beginning, another reversible step after that, and then finally a step that actually creates product, and the product in this case we consider to be the species E, whatever that is. So in this case there are 5 rate constants, 2 of which are reversible, and a total of, I think, 5 species altogether. And we're going to go through the sort of usual thing now for these kinds of problems. Write rate equations for each species in the mechanism, and then find an effective overall rate law for the formation of E that's consistent with the mechanism, assuming everything is at steady state. Well, all the intermediates are at steady state. All right, so that's our problem. Let me write down the mechanism over here. So A goes to 2B, and 2B goes to A with rate constants K1 and K minus 1. Then B plus C goes to D with rate constant K2 and the reverse of that. And then finally D plus A goes to E plus B. So we've got 5 elementary reactions overall and 5 species. First thing we need to do is write down the rate equations for each of the species. So dA, dt, well, let's identify the intermediates here. So it's the overall reaction is A plus C goes to E. And so B and D are intermediates, yes, and those are the only ones. So dA dt then is equal to, let's see, A appears in the first one, in the second one, and in the third one. There'll be 3 terms. So K1 minus K1 times A plus K minus 1 times B squared for this one, plus K, this is K3, K3 times D times A. Then for B, one of the intermediates, this is one of the things we're going to be setting to 0 in a minute, dB dt is then equal to 2 times K1 times A minus 2 times K minus 1 times B squared. That's for these 2 contributions. Then let's see, B appears in everything. So there's 5 terms, minus K2 times B times C plus K minus 2 times D. That was that term, those 2 terms. And then finally the last term, plus K3 times D times A. B is a product again in that for that reaction. Now dC dt is going to be equal to, let's see, C only appears here, I think, right? That's the only place, yes. So just one term, and it's a reactant, so minus KT, K2 times B times C. Then dD dt, another intermediate, is equal to, let's see, D appears here, and here, and here in 3 terms. So it's a product on the first one up here, K2 times B times C. It's a reactant here, minus K minus 2 times D. And it's a reactant here, minus K3 times D times A. And finally, the overall product of reaction, and this of course is going to become our rate law when we're through fooling around. So E, the EDT appears, E only appears one place, and so we're going to get K3, it's a product, times D times A. So A is a majority species, D is not, D is an intermediate, so really what this all boils down to is finding an expression for D in terms of majority species so we can eliminate that D from our rate law. All right, using the steady state approximation, then we're going to set this to 0, this to 0, so that's equal to 0, and then we're going to set this other one, this other intermediate, this one to 0. So that's also equal to 0. And as you've seen in earlier examples, it's usually a good idea to look at the relationship between these two, because oftentimes there's a close one and you can use one to simplify the other one. And that, I think, happens in this case. Let's see. There's K2BC. There's a minus K2BC. There's a minus K minus 2 times D. There's plus K minus 2 times D. There's a minus K3 times D times A, and there's a plus. So these three guys are the opposites, the negatives of these three guys. And these three guys together are all equal to 0, which means all these guys are equal to 0. Which means that just this first term is also equal to 0, which means that we can write that 2k1 times a is equal to 2k minus 1 times b squared, which means we can write that b is equal to k1 over k minus 1 square root times a to the 1/2 power. All right, so we have a relationship, or a useful relationship for one of the intermediates. Now we got to get rid of the other intermediate. That's the one we actually need up here, right? But we had to find this one first in order to use this equation. Now we're going to use this equation now to find d here. And so we have, what I'm going to do is take this guy and I'm going to factor that d out from this term. So k2 times b times c is equal to, minus d times k minus 2, plus k3 times a, that's equal to 0. That's just rewriting this equation up here. And now I'm going to substitute in here for b, so k2 square root of k1 over k minus 1 times a to the 1/2 power times c. And I'm going to switch this over to that side, so that's equal to d times k minus 2 plus k3 times a. And therefore, finally, we have d is equal to k2 square root of k1 over k minus 1 a to the 1/2 power times c divided by that stuff, which is k minus 2 plus k3 times a. All right, so now we have a useful expression for the intermediate that we actually need. Going back up here, let's get our final rate law now. So we have dE dt is equal to k times d. I'm going to substitute in there, and so that's k3 times k2 times square root of k1 over k minus 1 a to the 1/2 times c over k minus 2 plus k3 times a, and all of that times a here. And there's a little bit of simplification we can do, not too much though. I'm just going to multiply this a times that a to the 1/2 and get an a to the 3/2 power. So it's k2 times k3 times the square root of k1 over k minus 1 a to the 3/2 power times c over k minus 2 plus k3 times a. And that is our rate law in the steady state approximation for this particular mechanism. And I think we're done.